This video, whimsically titled Breathing Life into MO Theory, will explore what we are studying with regard to transition metal molecular orbitals and ligand molecular orbitals in the context of the oxygenation of hemoglobin. Red blood cells contain a substantial quantity of the protein hemoglobin, which absorbs oxygen as blood vessels pass through the lungs to give oxyhemoglobin. This is a reversible reaction. When the blood enters tissues which have a lower concentration of oxygen, the oxygen ligand is released. Hemoglobin is carried through the blood back into the lungs to repeat this catalytic cycle. The principal organometallic complex for oxygen transport is an iron heme center consisting of a heme ligand, which is a -2 charge with 2 nitrogens that are negatively charged. There are also 2 nitrogens which are neutral to electron donors. The carboxylate anions are not associated with the iron and are simply present for solubilization within the protein. In addition to the 4 nitrogens of iron heme, there is a 5th ligand which comes from a nitrogen of the amino acid histidine that is found within the protein. I'll show a video which depicts the iron heme structure within the protein hemoglobin. This is the structure of hemoglobin. The structure comes from the protein database and from a publication in the Journal of Molecular Biology, although lower resolution structures have been known since the 1950s. Max Perutz won the Nobel Prize in Physiology or Medicine in 1962 for the first crystal structure of hemoglobin. I'll expand on the heme portion. You can see that the heme is a planar ligand. The histidine nitrogen is oriented in an axial position. And on the opposite axial position, the 2 red atoms are dioxygen, O2. We'll follow up on this with line structure drawings. As shown on the left, once again, the iron heme substructure, along with the histidine ligand, and portray a simplified form so that we focus only on the 4 nitrogens of the porphyrin ligand, along with the histidine, with the heme ligand being -2, each nitrogen donating 2 electrons, and the histidine being a neutral ligand, but also donating 2 electrons. We can establish that the group 8 metal iron is in the +2 oxidation state with 6 d electrons. Adding in the 5 nitrogen ligands, this takes us to a total valence electron count associated with iron of 16 electrons. As oxygen approaches the iron heme complex, the current theory is that there is an initial single electron transfer from iron to oxygen to give superoxide and an iron 3 intermediate, which has the unusual D5 electronic configuration and 15 electrons associated with it. The bracket with the plus sign simply means that the positive charge is shared and delocalized throughout the iron, porphyrin, and even onto the histidine ligand. This intermediate is proposed theoretically. It has not been observed. It may even be a transition state, because some of the theory indicates that there is not a full single electron transfer from iron to oxygen. But what is known is what you saw in the crystal structure, which is that dioxygen is coordinated to iron with a 2-electron covalent bond, with the superoxide oxygen being negatively charged. This is also iron in the +3 oxidation state, 5 d electrons, and 17 valence electrons associated with iron. 1 electron short of the 18-electron rule. We'll analyze the molecular orbitals of oxygen, but first we'll turn to something more familiar by reviewing the molecular orbitals of dinitrogen. This is depicted on page 94 of the textbook. Nitrogen has atomic number of 7, so there are 7 protons and 7 electrons. 2 of the electrons come in the 1s orbital, and then the remaining 5 electrons fill the 2s and 2p orbitals as increasing in energy. We have the same situation for the second nitrogen. For the 1s orbitals, these are very low in energy. Technically, these also will mix, but the sigma is counteracted by the sigma star, bonding and anti-bonding orbitals. And from this point forward, we will focus only on the valence electrons in the second shell. For the 2s orbital mixing, we also have sigma and sigma star orbitals, which cancel each other out. The sigma bond of dinitrogen comes from mixing 2 of the p orbitals along one axis to give a sigma bond. Then the p orbitals along the y and z axes mix to form in phase pi molecular orbitals. The pi molecular orbitals are the highest occupied molecular orbitals. The LUMOs are pi star or pi anti-bonding orbitals. I'll show this for the valence electrons on spartan. This is dinitrogen, N2, and I'll show the orbitals for the valence electrons as calculated by Spartan. This is a sigma molecular orbital, then sigma star antibonding orbital, and then in contrast to the textbook, the pi orbitals are the next in energy. They are orthogonal to each other by 90 degrees. And the highest occupied molecular orbital is a sigma orbital. The LUMOs, as described in the book, are pi star, or pi anti-bonding. In any case, the overall valence electron count of the sigma bond the two pi bonds and the counteracting lower energy sigma bonds accounts for the non-bonded electron pairs on each nitrogen, as well as the triple bonding pattern between the nitrogen nuclei. This is a summary of the numerical energy levels, which we'll revisit again in this video. Now that we've reviewed dinitrogen, let's go to dioxygen, with the energy levels calculated by Spartan. Since oxygen is a more electronegative atom than nitrogen, the atomic orbital levels are lower, as are the resulting molecular orbitals. The sigma molecular orbital, coming from 2s plus 2s overlap, is so low in energy that it does not show up in the Spartan calculation. The lowest energy that does show up in the Spartan calculation is at minus 22.4 electron volts. Adjusting the inset for the numerical energy values, each oxygen atom has 6 valence electrons, so dioxygen has a total of 12 valence electrons. There are 2 electrons in a lower energy orbital. Then the first orbital that shows up on Spartan is the sigma antibonding orbital. Then there are 3 orbitals with similar energies, 2 pi orbitals, both at minus 15 electron volts. Then at minus 14.7 is a sigma molecular orbital. There are 2 more orbitals that are marked as A-HOMO, which are pi star orbitals at minus 8.1 electron volts. Notice that as we have been adding the 12 electrons into the orbitals, the top 2 energy orbitals have a single electron. So they are partially occupied or partially unoccupied. If we add an electron from iron 2 to one of these singly occupied orbitals, it will change the energy level of the orbitals as this occurs. I won't show superoxide anion, but if we add an electron, then we only have one singly occupied orbital, and that is the highest energy orbital that contains any electron density. It is this 2 electron pair at minus 8.1 electron volts in this diagram that will be donated to iron 3 to form the iron-oxygen bond of oxyhemoglobin. Let's now look at carbon monoxide. You've already seen carbon monoxide. On the right, I list the energy levels. Carbon has 4 valence electrons. Oxygen has 6 valence electrons, so the bonding will involve 10 valence electrons. Carbon monoxide is actually isoelectronic to dinitrogen, which also has 10 valence electrons. Let's look at the orbitals calculated by Spartan. The lowest energy orbital is sigma bonding. The next orbital is sigma antibonding. Then there are 2 pi molecular orbitals of the same energy levels. And then a sigma bonding orbital derived from the p orbitals. Here's the LUMO of carbon monoxide, 2 orbitals at the same energy level, with larger lobes on carbon. I'll now show the numerical energy levels for nitrogen, for carbon monoxide, and for oxygen. If we compare the highest occupied molecular orbitals for nitrogen and carbon monoxide, you will see that carbon monoxide has a higher energy HOMO, therefore it will be more reactive with electrophiles. It will be more likely to donate electrons to an empty orbital. Dioxygen is an interesting case because the highest energy orbitals have a single electron within them, but that energy level is higher than that of carbon monoxide. This oxygen can both donate an electron and accept an electron into either orbital at minus 8.1 electron volts. Returning to the video of hemoglobin in the oxygenated form, note that the O2 ligand is coordinated to iron in a bent fashion. If we examine the shapes of the molecular orbitals of dioxygen, the highest occupied molecular orbital has a pi star shape. Therefore, this fits with an orientation of oxygen donating electrons to iron in a bent fashion. Now let's consider what happens if instead of oxygen, or in competition with oxygen, carbon monoxide is present. We all know that carbon monoxide is a toxic gas produced by incomplete combustion of hydrocarbon fuels, whether it's coal, oil, gasoline, natural gas. I'll show the HOMO. This has a large lobe on carbon containing 2 electrons that will donate electrons to an empty orbital on iron. Furthermore, the LUMO, and there are 2 of them, has the pi star geometry. So the bonding may be strengthened by back bonding of a filled d orbital on iron with an empty pi star orbital of carbon monoxide. The crystal structure of carbon monoxide complexed with hemoglobin has been determined. This is hemoglobin, once again, should look familiar, but if we zoom in on the heme, this is now carbon monoxide complexed with iron. The red atom is oxygen, the green atoms are carbon. Notice that the coordination is very nearly linear, which is in line with the MO theory. If we return to the line drawing of iron heme, this is the iron heme shown again, now with carbon monoxide as the electron-donating ligand. The HOMO of carbon monoxide will donate electrons to an empty orbital of iron to form a sigma bond between iron and carbon of the carbonyl. Carbonyl complexation does not change the oxidation state of iron, so it remains iron in the +2 oxidation state. But now this fulfills the 18 electron rule. Furthermore, there is back bonding orbital overlap between one of the filled d orbitals of iron 2 with the pi star orbital of carbon monoxide. I'll conclude by sharing some kinetic and thermodynamic data from the literature. We'll start with the kinetics of ligand association. The rate constant for association of dioxygen is significantly faster than the rate constant for association of carbonyl. Oxygen bonds about 40 times faster than carbonyl. There's a slightly lower activation energy for oxygen coordinating with iron. The key to this is the dissociation rate constant. Oxygen dissociates about 4,000 times faster than carbon monoxide. There's a higher activation energy for carbon monoxide dissociation. So even though carbon monoxide binds much more slowly to iron than oxygen, once the carbon monoxide is on iron, it does not dissociate very rapidly at all. There is a high energy barrier to carbonyl dissociation. Here are the thermodynamics for oxygen versus carbon monoxide association with hemoglobin. Both processes are exergonic and exothermic, and of course with two molecules coming together to form one complex, we expect that the degrees of freedom decrease, therefore there's a negative entropy term. But with carbon monoxide, the association is much more exergonic than for dioxygen association with hemoglobin. And carbon monoxide association is also more exothermic. The combination of kinetics and especially the thermodynamics, along with the molecular orbital explanation, shows that carbon monoxide will tie up hemoglobin so that the concentration of hemoglobin available for coordination with oxygen is diminished. Therefore, the mechanism for delivering oxygen to the tissues is inhibited with a lower concentration of oxyhemoglobin available. This is the chemical basis for the toxicity of carbon monoxide. This concludes the video on breathing life into molecular orbital theory.